In this video, we will look at how to determine what the stress in a beam is due to bending. And so effectively, we will derive what bending stress is for a given applied moment. Now, this is a very important topic for structural engineering because there are a lot of beams in structures. So that could be something which is supporting the floor of a building or the road deck of a bridge. And so lots of beams, and all of those beams, if they've got some transverse load, or like what we have here, some pure bending, they will be subjected to some moment, and that moment will give rise to some internal stress from bending. And so our job as a structural engineer is to be able to work out, what size beam does this need to be in order to resist the moment and keep the stresses in the beam down low. So in this video, we will go through and we'll derive a case for what the cross section, for what the bending stress is at any point along a cross section of a beam for a given moment. And it's actually is quite a very elegant equation, which carries over in all cases for bending. But in order to get there, we'll start with this very simple case of just a simply supported beam applied, with two applied moments. So it's under pure bending. And one of the things that we would going to do when we start this derivation is we'll effectively slice up this beam into a series of cross sections. And so we can term these as planed sections. So you think of it like there's a plane cutting through the beam. And so if we jump to the three-dimensional world and I take out my foam beam, we've got these cross sections driven here. And again, these are what we term planed sections. So it's like there's an XY plane cutting through the beam. Well, if we apply pure bending to it, so we take a moment and we apply it from both ends, one thing that we notice is how the beam deforms. So obviously the top gets shorter and the bottom gets longer. But if we look at the cross sections, so those plane sections, one thing to keep in mind is that they really just stay straight. What we term as plane sections are remaining planed. So the only thing that they're doing is that they're rotating. So they're not, turning into an S. They're just staying straight and then opening or closing. So just like that. So these plane sections are remaining planed. And this is really the key to this derivation. It's the sort of key insight when it comes to determining bending stress, is that if your plane sections remain planed, everything that we're going to do from here on will work, and then you'll be able to determine what your stress is. And in fact, plane sections remain planed for most beams under sort of standard design loading. So it means this is going to be a really useful equation for us. So just to summarize there, as we bend this beam, the cross section, so these plane sections remain straight, and they're just rotating, just rotating around. And we would call that, plane sections remain planed. So not only are they rotating, but they seem to rotate, if we're under constant bending here, they seem to rotate kind of at a constant rate. In fact, you can sort of consider this like they're effectively rotating around, some point O, where you've got bending in a circle, and then all of these plane sections are effectively coming back to some point right here, up above them at some distance away. And we would call that distance, say, R, for the radius, because it's bending in a circle. And so, as I said, so that's sort of our first key insight, is that plane sections remain planed. The next thing that we can think about is really what's happening to this cross section. So, as I said, if we're bending it, pure bending in this direction, the top is getting shorter and the bottom is getting longer. But if we sort of think, well, if we take this section, we sort of cut it up, and we have some, little cross section area in there. If we pull this out and say that we'll put some coordinates to this, where we'll say y is going up and down across the cross section, z is along the length of the element, and then x is going to be across, so transverse to the beam. Well, the top is getting shorter and the bottom is getting longer. But for the top to get shorter and the bottom to get longer, if your plane section is remaining plane, means it's staying in a straight line, well, it's going to get shorter and longer at a constant rate, because really all that's happening is, we've got some cross section. So you can think of, you've got a plane section like this. I'll draw it here in black. So you've got a plane section there and a plane section like this for some, little distance dz. So you can think of that as like your gap here. If you watch those two, as we bend them, yeah, the top gets smaller and the bottom gets longer, but, because all they're doing is plane sections remaining plane, they're moving at a constant angle, which means that at some point in the middle, well, you have no change in length. And so if we're to sort of write down, we'd have the top would be getting, the shortest. And then you'd be shorter. And then short. And then in tension, you're, longest. Longer. Long. And then somewhere in the middle, you have no change in length. And that's all really good. And in fact, we'll come back to this point which has no change in length, because it is special to us, and it will help us out with this derivation. And we call this no change of length, the neutral axis. Now, again, we've sort of broken all of this down, and we've seen that, well, parts get longer, parts get shorter. And if we cut this into a series of cross sections, and we think of this really as like a series of tubes or a series of axial problems, where if you're getting shorter and longer, well, how do we think of that if you've got an element which is getting shorter or getting longer? Is it's changing in length. So if we think that we have some, change of length, well, the change of length over the original length, that just equals strain. So all of a sudden, we've now gone from sort of some deformation to now the structural mechanics concept of we have some strain. And this means that at the neutral axis, there is no strain. At neutral axis. Because there's no change in length. And so this could be something that's really, really useful. The other thing to sort of keep in mind that what we'll have, and I'll just sort of state it, is this special point, this neutral axis, where there's no change in length, it occurs at the centroid. And this is neutral axis. Occurs at the centroid. So now that we sort of have some relationship between, or we have this understanding that the section is going to, parts of it will get longer, parts of it will get shorter, and we know that this relationship is effectively going to be linear across the cross section, right? Because if these plane sections are remaining plane and they're just changing angle, it means that the distance will change at a constant rate as you move away. And so we can set this up. And then what we kind of want to know is, well, how much shorter does this get at the top section versus the neutral axis? How much longer does it get at the bottom versus the neutral axis? So what is our change of strain as we come down the section? So to do that, we'll just sort of set up another little diagram. So if we have, what the derivation for how the strain changes over the cross-section length, we'll have the same beam, which is being bent in pure bending. In fact, what we'll do is we'll just we'll put these moments back on there. And as we said, we had some, it was bending, and it's effectively bending around some point O. So if we treat this and we treat, some O and some distance R, and we say that the distance R from the point which all of these plane sections is rotating is between that point and the neutral axis. And that we'll have some change, and basically what we're looking at is some change in the angle. And if we think about what our arc length is, what this change from here to here is, our arc length is simply going to be the radius r times the included angle in here, so this d theta. So if, and again, we'll look at our coordinates are going to be y and z, and we'll say that our zero coordinate for our y is going to be right down here at the neutral axis, and we're going to point it down, and z is going to go this direction. So as we sort of thought, from our previous diagram here, we want to look at what our change of length is over, some small area, dz. And so if we want to look at what our strain is along the length of the beam, so change z, it would be the strain in the z direction, so along the beam. It's just going to be the change of length of that beam over the original length of that beam. Well, that makes some sense. And so at the neutral axis, well, this original length L is simply going to be equal to this radius r by which we are rotating all of our plane sections around, multiplied by this angle d theta. And this gives us what the length of this sort of infinitesimally small delta z is once it's been bent around. Well, and then we'll set up our coordinates where y equals 0 at the neutral axis. And so if what we want to do is sort of find out what our change of length is as we come away, we can set up this this equation where the strain along the beam is simply going to be, and now all we're going to do is just sort of work out from geometry as we move further away how this arc length changes. And so really it's just going to be, as r plus y, so as we move away from the neutral axis, we want to know what that arc length is, d theta. And then because we want to know what our change of length is, well, we want to know what it is relative to our original length. So, if L is, L1 minus L naught, well, L naught, the only thing which is not, changing its length is this neutral axis, right? So right here in the middle of the beam, it doesn't change any length. It doesn't get longer or shorter. It just stays the same length. It just rotates around. It's only the top and bottom that change length. So if this is our original length, and then we have minus r d theta, so this is effectively the same as delta L. And then we want to go over our original length, which is just simply going to be r times d theta. And this is going to be equivalent to L. And so again, all of this is doing is just setting up strain, where we have our original length, and then we want what our change of length is going to be. And our length is simply going to change as a function of moving away from the neutral axis. So if we move away, the beam gets longer, so our arc length gets longer. If we move towards this sort of center of rotation of these plane sections, y is a negative, and so our arc length gets smaller. So all we're doing is the only strain which is happening is simply from geometry, from those plane sections rotating like so. And again, this all just comes down to just simply defining strain in terms of the arc length. So if we do a little bit of sort of calculus. Oh, and maybe what I'll do is I'll just, for sake of this y is at the neutral axis, I'll draw you a cross section here too, just so be neutral axis, and y is going this direction, just like we have there. So if we do a little bit of solving and simplifying of this equation, effectively what we can do is we can factor out the d theta, and then we would have equals d theta r plus y minus r over r d theta. The d thetas cancel out, those two r's cancel out, and we get that the strain across the cross section is simply going to be equal to y over r. And we give r this sort of, and which again is quite simple there. That it's really just going to be, we have a strain which is just proportional to the distance away from the neutral axis, which is really just sort of mathematically proving what we've seen intuitively here, that your strain increases as your distance away from the neutral axis increases. And so, and we in fact give this r a special name, and we call it the radius of curvature. And it is in, some distance. So units equal distance. And which, again, simply means that your the strain, which is going to be in your beam, is going to be inversely proportional to how much you've bent it. And in fact, we tend to call, we'll simplify this for yet another term, and we'll call phi is going to be 1 over r. Instead of the radius of curvature, we call this curvature. And so curvature is related to rotation, but a little bit different though. Sort of, 1 degree removed. And then if we have this, we'll end up with what we call our moment curvature relationship. So curvature times your distance y from the neutral axis. And we'll use this simplification here coming further along. So what we can see simply from this is that the strain varies linearly with distance from the neutral axis. And so that means it's just going to vary linearly with depth. So, and in fact, this here is actually the definition of what means that plane sections are remain planed. And so that's worth actually writing down. So the definition of planed sections remain planed is that the strain profile is linear. Strain file over the depth of the section is linear. So let's draw out what that means. So, say that we have our cross section here. And we've got some neutral axis. Now, if we're to draw what the strain profile is, coming across here, well, this is our cross section here. So we've got our distance y down the middle. It means that if we're to plot what the strain is, it'd simply be a straight line where y is coming down. And the other thing that we would find is that the angle of this strain profile, so say this is our strain with respect to y, this angle is simply going to be our curvature, equal to curvature equal to 1 over the radius of curvature. And then what you can kind of see quite, and that would make sense too, right? So if you think of this as like an XY plot, well, for every y you come up, you're going to multiply over some distance based upon some, this is like the slope of your line. This is like mx plus b. This would be the factor that you're changing your strain by, which is just simply going to be this curvature. So, all right, well, that's all well and good. So now we know how to go from, some physical bending, so some applied moment, to some physical bending, to the fact that we're going to get shorter and longer based upon our distance away from the neutral axis, turning that into a strain. And now we have that relationship of strain relative to our cross-section. Well, that's all well and good, but I'd said, like, we care about stresses, right? So how do we go from our strains to our stresses? And that is simply by looking at the fact that, well, let's look at an elastic material first. For elastic material, we'll call it linear elastic. And if we're to look at a linear elastic material, let's look at sort of the stress-strain behavior of that and see if we can't use that fact to sort of relate, what our strain profile is to what our stress profile should be. So, say we've got, this will be some axial material, and it'll be pulled in tension. This axial material works out just fine for us because, again, remember, we're just treating each of these little sections like it's effectively a long tube, and we're just looking at its linear strain. So, let's look at our linear stress-strain behavior. So, if we're pulling this material and it's elastic and it has not yielded, well, its stress-strain behavior will simply be a straight line. And it'll be a straight line whose slope is Young's modulus. So if we use this, and we use the fact that from Hooke's law, that the stress is simply going to be the Young's modulus multiplied by the strain, which is all this is saying graphically. Well, we can use this and the fact that we have a relationship with strain to determine, well, how is our stress going to change with the change of curvature and with the change of distance away from the neutral axis. So if we have this, so it's just a little bit of algebra and substitution, then, if strain is equal to curvature times y, we can sort of rearrange, take Young's modulus over here, then we would have that stress over Young's modulus is going to equal curvature multiplied by the distance away from the neutral axis y. And so stress equals Young's modulus, modulus of elasticity, times curvature times y. And so what does this mean? This means that bending stress has a linear stress profile because, again, this is a constant, this is a constant. The only thing that changes is the distance away from the neutral axis. So remember, this is equals distance from neutral axis. So that means that bending stress has a linear profile. So what would that look like? Well, if our strain profile, again, we'll draw our little cross section in here. Draw the neutral axis and draw some lines across. So if our strain profile looks like this, well, then our stress profile over the same location will also look like this, where we have our strain with respect to y, and y is at the neutral axis, and this coming across is the neutral axis. And that means that, the bottom, you'll have some tension stress, and at the top, you'll have some compression stress. So you'd have sigma in compression and sigma in tension. So that's all well and good. So we've actually now discovered quite a bit here, where we know that both our strain and our stress for an elastic material are going to be linear with respect to depth, and that they're just simply going to change with respect to the distance away from the neutral axis and the curvature, and the stress will also be related to Young's modulus. So that's really good, but we still don't really have a way to relate this internal stress to what our applied moment is. So effectively, we don't really have a way to go from our moment to our radius of curvature. Now we've got a few clues. I mean, we've got a Young's modulus, so we have a stiffness in there. But again, we want to be able to relate what we've got here to what our applied moment is. So in order to do that, I'm going to redraw this, where we're going to actually put the stresses both on the same side, but we'll have one in tension and one in compression, and I'll show you why. So if we have our cross section, so need to relate stress to applied moment. All right, so if we have our cross section here, and it's got some, say we take a cut, say it's got some bending stress and some tension stress, and we'll just draw them coming out of the cross section like this, where you have your tension there, and your compression coming in like this. Then if we're to draw our cross section, well, we would have cross section here. Again, this is effectively just flipping the tension side, so it's on the same as the compression, just as a pictorial representation. And the reason that we'll do that is that, well, we have to remember one of the key rules of our of doing structural engineering, and that is that our external forces have to be balanced by internal forces, so internal stresses. And so the external force that we have here is an applied moment, right? So that's what we started all of this with, was some applied moment. Well, this moment, if you take a free body diagram, it's going to expose some bending stress, which you'll have some bit in tension, and you'll have some bit in compression. And if you look at the sort of distribution, we know this is a linear distribution. We know that there will be some equivalent, some resultant force, C, in compression, and some resultant force, T, in tension. And so we can use this fact to help relate back to, our moment and what our stress is. So, at the neutral axis here, the section has to be in equilibrium. So we'll say that, and we'll just write this down. So for the neutral axis at the centroid, and section must be in equilibrium. And that means that C has to equal T. So this compression force has to equal this tension force. Again, as an aside, so the reason the neutral axis has to be at the centroid is if you think about this resultant force, well, it's sort of the area of the stress multiplied by the width. So this sort of volume of stress has to equal this volume of stress above it. So the volume of stress and tension has to equal the volume of stress and compression. The only place where that's equal, because they're based upon the cross-section, is at the centroid. So you have the same amount of area above as you do below, and then you're going to have this linear stress profile. So that means that you sort of by definition will always have your neutral axis at the centroid. So if you remember nothing else, just remember it's at the centroid, and it's because the compression and tension have to be balanced. So we're not far away from being able to sort of work out what our sort of moment is. And we just have sort of one last little thing to keep in mind, is that there's no net axial force. And what I mean by that is, when we're just bending, the forces are all sort of equalized, and they're in, and it's only bending which is causing. We don't have any axial force also pushing this into compression or pulling it into tension. So this is going to work for our just simple axial force here. So if we have this, again, now we've set up kind of all the pieces, and what I'm going to do is I'm going to draw another little diagram, and we're going to think around, what this stress is and how it relates back to moments. And so we're going to go kind of with a similar diagram to this, where we're going to look at just one little section, and we're going to look at how this affects across the entire cross-section. So effectively, we're going to do a little bit of calculus. All right, so in order to get here with this no net axial force, we'll draw our little cross-section. And we'll discretize it into a bunch of little blocks. And so if we think about, and we need to, compression is equal tension. So for this, we need to make sure that we've got forces in equilibrium. So if we've been thinking about this cross-section as really a series of, little axial problems, we did it here in thinking about the strain, we did it here in thinking about the stress-strain relationship. Well, let's continue on that, and let's think about, some axial force. So, again, we'll take some tiny little cross-section here, and we'll call that dA. And in compression, it has this tiny little stress, sigma c. And the neutral axis will be down here. So we've got we'll set up our coordinates. Y is going down, neutral axis is right there. So we've got, this compression on the top, and that's, some stress. Well, stress times an area is going to be a force. So we can say that we've got some tiny little force right up here. We'll call it dF. And that's going to equal our stress multiplied by our area, a little tiny bit of area. So tiny bit of force times a stress. So tiny bit of stress times a little bit of area. It's going to be a little bit of force. And so, as I said, this sets up our small discrete bit. If we want to see what this force is over the entire cross-section, what we would do is we would integrate it over the entire cross-section, both across the width and down the depth. So if we integrate over the whole area, this little force, that'll give us the integral of this stress times dA. And as I said, there's no net axial force. So for no net axial force, this all has to equal 0. So for no net axial force, force is equal 0, then all of this has to equal 0, which means that A times dA equals 0. So it says sum of the forces. We'll say it's no net axial. So over the area, dF equals 0. All right, so we've set this up. This is just really simply the calculus version of just saying that C equals T and there's no other applied force. So this is just doing some calculus to say this and give us some mathematics to set this up. Now, here comes the real meat of all of this, is we need to find the moment-stress relationship. Moment-stress relationship. All right, now setting all of this up, we'll do a little bit of calculus. So if we know that df equals sigma times dA, well, if we want a moment, and we want to know what the moment of this tiny force is to some, area, well, it's just really the moment between df, or this force here, df, and the neutral axis is simply going to be the distance y away. So our little tiny moment, dm, equals the distance y away from the neutral axis, could go down, could go up, multiplied by df. All right, cool. So this is sort of our two equations. Well, if we want to substitute in, we can multiply y by both sides. We could get df times y equals y sigma times dA, so stress times the distance away from neutral axis times our little tiny bit of area. So again, this is just, substituting this in. Now, this only gives us what this tiny moment is between the neutral axis and this area. So this is only really our relationship between what the stress is. And let me just rewrite this one more time just so we can just get directly back to moment, equals y sigma dA. There we go. So this is only one tiny little bit of the cross-section, its relationship of its moment to its stress. But you see, we're getting much closer. So we're getting some relationship between the moment and the stress, but only one little bit. So if we want to go from one tiny piece of a cross-section to the whole cross-section, what do we have to do? We have to integrate. So if we integrate, we'll take integral of dm over the entire area equals the integral over the entire area of y times the stress times dA. And then, the little tiny moment. So if we integrate over the whole area, this is going to equal the applied moment. And so we'll end up with the moment equals somewhere over the area of y times our stress times dA. Now what we are going to do, we're going to pull a little trick. And we're actually going to use our relationship between our stress and our curvature. And so this will give us what our change of stress is with respect to our distance y. So m equals a times y times e times our curvature times y over dA, and where this is simply the fact that stress equals Young's modulus times curvature times y. All right, we're going to do a little bit of rearranging. So our curvature and our Young's modulus are constant, so we can just pull those out in front of the integral. So we have m equals Young's modulus times curvature equals a y times dA. M equals e times curvature a y squared dA. Ooh, all of a sudden, something has popped out here from the equation. This integral over the area of y squared over dA should look familiar from our properties of plane sections. This is the second moment area. also known as I, the moment of inertia. So we know how to calculate this. This is just a constant based upon the cross-section, which now all of a sudden means that we have some relationship between our moment and then what our stress is going to be and our moment of inertia. So m equals Young's modulus times curvature times I. And so we can do a little bit of rearranging. We can have m over I is simply going to be equal to, well, we've got E times curvature. E times curvature, which is also equal to sigma over y, just doing a little bit of rearranging, E times curvature is sigma over y, which means that our stress from bending is simply going to be m times y over I. The bending stress is simply going to be a relationship between the bending moment, the distance y away from the neutral axis, and the moment of inertia of the cross-section. So all these things are actually pretty straightforward to find, and this is what makes this sort of moment curvature relationship so elegant. Is from just simply thinking around plane sections remain plane. Think of that this as a series of axial problems where we're getting shorter or longer in a linear fashion relative to our neutral axis. So that gives us a strain. We can then go from a strain and look at our stress-strain relationship. We know that our stress is linear. And then we know that if we don't have any applied axial force, then the section is going to be in equilibrium as long as the compression and the tension portion of our stress equal our applied moment. And then we can just use that with a little bit of calculus to work out this really quite simple and elegant relationship that the stress in bending is equal to the moment times the distance away from the neutral axis divided by I. So if we're going to use this, I'm going to just sort of end this video with just a little bit of a procedure of how do you find these and how do you use this and how do you find bending stress. So procedure for bending stress. So the first thing you want to do is draw your free body diagram. This is always a good way to start, and this is how you need to work out what your reactions are and what your demands are. Your second is draw your bending moment diagram. And that's going to give you what your moment is. And then you need to find your centroid. X bar, Y bar, and that'll gives your value Y. And then find your moment of inertia. And then once you have that, it's just simply a plug and chug. Find sigma equals my over I. So I hope you found that helpful, and I hope you find this procedure sort of a nice guidepost in working out what your bending stresses are. And with that, thanks for watching.